Section 10.2, the hyperbola. A hyperbola is the set of all points in a plane, the difference of whose distances from two fixed points, called the foci, is a constant. The line through the foci intersects the hyperbola at 2 points called the vertices. The line segment that joins the vertices is the transverse axis. And the midpoint of the transverse axis is the center of the hyperbola. The standard form of the equation of a hyperbola with center at the origin is x squared over a squared minus y squared over b squared equals 1. This version has its two branches crossing the x-axis, but we could also have y squared over a squared minus x squared over b squared equals 1. And this version has its two branches crossing the y-axis. It's important to note that when we studied ellipses, a squared was always obtained by taking the larger denominator. But for hyperbolas, a squared is always the denominator of the positive fraction. The vertices are a units from the center. The foci are c units from the center. Since the denominators of our equation give us a squared and b squared, we will need to find c using a special formula that relates them. C squared equals a squared plus b squared. The alternative equivalent formula of b squared equals c squared minus a squared is typically used when we are given the foci and the vertices and we need to find b. It's important to note that the equations that relate a squared, b squared, and c squared are different for hyperbolas and ellipses. Example 1. Find the vertices and locate the foci for the hyperbola with the given equation. We begin by observing that the first fraction, the positive fraction, has an x squared up top, and that tells us our vertices will be on the x-axis. More specifically, that denominator is a squared, which is 25. That gives us an a value of 5. So our vertices will be 5 units to the left and right of the origin. To locate the foci, we need c. We can use our c squared equals a squared plus b squared equation. We obtain a squared and b squared from the denominators in our equation. And 25 and 16 add to 41. Next, we find c by taking the square root of 41. To plot these points, we'll approximate the square root on our calculator and obtain 6.4. This puts one focus at negative 6.4 and the other focus at positive 6.4. Example 2. Find the vertices and locate the foci for the hyperbola with this given equation. You may notice that our first fraction, the positive fraction, now has y squared in the numerator, yet the values for a squared and b squared remain the same as the previous example. This tells us that the vertices and foci will be on the y-axis. A squared is obtained from the positive fraction, so a squared is 25 and a is 5. So the vertices will be 5 units above and 5 units below the origin. To locate the foci, we need to find c. We use c squared equals a squared plus b squared with a squared of 25 and b squared of 16. Those add to 41, so c squared equals the square root of 41, giving foci that are approximately 6.4 units up and 6.4 units down from the origin. Example 3. Find the standard form of the equation of a hyperbola with foci at 0, negative 5 and 0, 5, and vertices at 0, negative 3 and 0, 3. Because the foci and vertices are located along the y-axis, this hyperbola's equation will have the y squared term in the numerator of the positive fraction, the first fraction. We need to find a squared and b squared, and we can obtain a squared by noting that the value of a is the distance from the center to the vertex, which is 3. Since a is 3, then a squared is 9, and we can place that in our equation. We need to find b squared, but we do not currently have that value. We can, however, obtain c and c squared from the values of the foci. Since the distance from the origin to either focus is 5, then c is 5 and c squared is 25. Knowing a squared and c squared, we can find b squared using the formula b squared equals c squared minus a squared. B squared equals 25 minus 9, which equals 16. And we are now ready to place b squared into the hyperbola's equation. This results in the equation of y squared over 9 minus x squared over 16 equals 1. We have discussed plotting the vertices of a hyperbola and observed that its two branches open away from each vertex. Now we'll learn how to determine if these branches open sharply or open gradually. Each hyperbola has two related lines called asymptotes. Although the asymptotes are not part of the hyperbola itself, they guide us in drawing the branches accurately as we move away from the vertices. As the two branches of the graph of a hyperbola get further from the vertices, they approach the asymptotes. Let's explore the effect of b squared on the branches of a hyperbola. If we have the equation x squared over 4 minus y squared over 1 equals 1, then a squared equals 4, so a equals 2, and therefore the vertices are at plus 2 and minus 2 in the x direction, and we draw our hyperbola. But how do we know how to draw the asymptotes? Well, for that, we look at b squared is 1, so b is 1. So we draw a rectangle 1 unit above and 1 unit below the origin, and the rectangle also goes through the vertices. Then we draw the diagonals and extend them. As we move away from the vertices, we have the hyperbola approach those asymptotes. So this is what it would look like if b squared equals 1. Now let's take a look if b squared is equal to 4. If b squared is 4, then b is 2. So we go up 2 and down 2 to draw our rectangle. And then we draw the asymptotes. So the hyperbola is opening up more gradually. If we go from 4 to 9, then b squared is 9, b is 3, and so our hyperbola opens up even more gradually. We can go from 9 to 16, and from 16 to 25, and from 25 to 36. Notice that when b squared is large relative to a squared, our hyperbola opens up gradually, and when b squared is small relative to a squared, our hyperbola opens up more sharply. Since the hyperbola's two asymptotes are lines, you may be asked for the equations of those two lines. When x squared is in the positive fraction, the equations of those lines are y equals b over ax and y equals negative b over ax. When y squared is in the positive fraction, the two equations are y equals a over bx and y equals negative a over bx. The steps for graphing a hyperbola are to locate the vertices, use dashed lines to draw the rectangle, use dashed lines to draw and extend the diagonals of the rectangle, and then draw the two branches of the hyperbola starting at the vertex and approaching the asymptotes. Example 4. Graph and locate the foci of this hyperbola and find the equations of its asymptotes. First, we'll locate the vertices. Since the equation's in this form, a squared is 36 and b squared is 9. The vertices are associated with the positive fraction, so since a squared is 36, a is 6. So we'll go 6 units to the left and to the right of the origin to find our vertices. We plot the vertices, and now we'll draw a rectangle. A squared is 36, and b squared is 9. So again, we go 6 units in the x direction, and we go up and down 3 units to draw our rectangle. And then for step 3, we'll draw and extend the diagonals of the rectangle. These are our asymptotes. We were asked to find the equations of the asymptotes. So our slope will be m equals plus or minus b over a. Remember that slope is the change in y over the change in x, so that can help remind us that that 3 is obtained by taking the square root of what's underneath the y term, and the 6 is found by taking the square root of what was underneath the x term. The slope reduces to plus or minus 1/2, so the equations are y equals 1/2 x and y equals negative 1/2 x. We then can draw the two branches of the hyperbola starting at each vertex and approaching the asymptotes. We're also asked to locate the foci. To do that, we need to find c, so we'll use our c squared equals a squared plus b squared, where a squared is 36 and b squared is 9, and that adds to 45. So c is the square root, which simplifies to 3 radical 5 and approximates at 6.7. So the foci are shown here in simplest radical form and in approximate form. Example 5. An explosion is recorded by two microphones that are 3 miles apart. Microphone M1 receives the sound 5 seconds before microphone M2. Assuming sound travels at 1100 feet per second, determine the possible locations of the explosion relative to the location of the microphones. To begin, note that the explosion's possible locations form a hyperbola with foci M1 and M2. The explosion will be on the branch of the hyperbola that is closer to the microphone M1. Why do the possible explosion locations form a hyperbola? Recall that a hyperbola is the set of points where the difference in distances to the two foci is a constant. To help us visualize this, suppose the location of the explosion is here on our graph, and it takes 2 seconds for the sound to reach microphone M1. If it takes 7 seconds for the sound to reach microphone M2, then the sound reached M1 5 seconds sooner than M2. It is also possible that the explosion occurred here and took 6 seconds to reach M1 and 11 seconds to reach M2. Again, the sound reached M1 5 seconds sooner than M2. The set of all points where the difference in the distance to the two microphones is 5 can be modeled by the equation of a hyperbola. Now let's return to our question and work through some details involving the units we might use for distance. Before we locate the foci, observe that one distance is given as 3 miles and the other distance must be calculated from the 5-second time difference. For simplicity and consistency, we will convert both distances to the same unit. And since the speed of sound is provided in feet per second, we will convert all distances to feet. Recall the conversion factor of 5,280 feet in a mile. So to convert miles to feet, we multiply by 5,280. 3 miles is equivalent to 15,840 feet. To determine the distance traveled in 5 seconds, we will use the speed of sound, which is 1,100 feet per second. By multiplying the time by the speed, we determine the distance traveled in 5 seconds is 5,500 feet. Next, we locate the foci, which are 3 miles apart, and represented by M1 and M2 on our graph. And though that means one focus is located at positive 1.5 miles and the other at negative 1.5 miles, we found that it'll be best to convert miles to feet. By multiplying by 5,280, we calculated the foci are 15,840 feet apart. Therefore, half of this distance is 7,920 feet, placing each focus 7,920 feet from the origin. Now let's consider the fact that M1 receives the sound 5 seconds before M2. Since the sound travels at 1,100 feet per second, we can multiply 5 times 1,100 to determine that M1 is 5,500 feet closer to the explosion than M2. The difference in the distances is 2a, so we can calculate a and a squared. 2a equals the 5,500 foot difference. We divide both sides by 2 to get a, then we square both sides to find a squared is 7,562,500. We found that the distance from the center to each focus is 7,920 feet. Thus, that is our value for C. And squaring both sides gives us C squared equals 62,726,400. And now we can find B squared. We use the equation that relates A squared, B squared, and C squared, which is B squared equals C squared minus A squared. We substitute our values and subtract, which gives us B squared equals 55,163,900. We can now place A squared and B squared into our hyperbola equation. Therefore, we have found the explosion lies on this hyperbola. More specifically, the explosion will lie on the branch that is nearest to microphone M1.